Yes, what I'm going to report on is a large-scale longitudinal study of flaky tests that I had the pleasure to contribute to, along with colleagues from the University of Illinois at Urbana-Champaign, Peking University, and Northeastern University. Since Martin has already given us a brilliant introduction into flaky tests, I think I can go a little bit faster here. But nevertheless, I would also like to add an additional perspective why flaky tests are problematic. Let me first briefly tell you again what flaky tests are. Flaky tests are tests that can both pass and fail when run in the same test scenario. What we mean by test scenario is the same source code on the test, the same test code, and there are also no changes to the test driver, for instance. Why are these flaky tests a problem? These flaky tests are a problem because if a developer writes code and of course also test code, and the developer commits his or her changes to the CI pipeline, then the CI pipeline gets back to him with the test results. And these test results indicate whether any changes that have been made are potentially problematic or not. So in this case, for instance, the test T1 says pass and the test T2 says fail. Now, this is a useful technique. However, if in the presence of flaky tests, T2 may not actually fail because of a defect that the developer has introduced, but simply because the test code is flaky. And because of that, that can cause a lot of confusion to the developer, who may start, for instance, searching for the defect that is actually not in the code. So that's the first problem of flaky tests. It wastes developer time. But there's also a different perspective. If developers see these flaky tests fail and pass non-deterministically often, then they stop trusting their test results. And what may happen is that they actually ignore test failures. And once developers start ignoring test failures, then it's not a long way to not writing tests anymore altogether. So this is an additional problem, and it's a big problem that has been acknowledged by many different software organizations and companies, such as Microsoft, Mozilla, Facebook, Google, and so on. Since it is a big problem, some of these organizations are actually trying to identify these flaky tests in advance, or at least as soon as possible, before they can flake in production and distort the developer's work. For instance, Mozilla and Netflix are using flaky test detection mechanisms to detect these flaky tests up front. These detectors that are currently being used usually fall into 3 different types. What these different detectors have in common is that they all repeatedly rerun the tests. And they do that under different conditions. So for instance, there are detectors that isolate tests from one another to make them fail. Then there are detectors that change the order in which tests are run to make them fail. And then again, there are detectors that change the underlying implementation of an underdetermined specification, such as the iteration order of a hash set, for instance. Now, the good thing about these detectors is they have proven to be effective, so they work. We can identify flaky tests using these detectors. That's a good thing. However, they also have a downside. As I already mentioned, most of these detectors are based on rerunning tests. And of course, these reruns entail certain overheads. Now, the problem is that these overheads possibly occur on the critical path, so during regression testing. And as you may know, there are lots of techniques that people are investigating and try to develop to actually reduce the amount and effort of regression testing. So it is kind of counterproductive to add additional reruns to identify flaky tests. At least we do not want to do that on every single commit. So this is basically the question where our study started from. We ask, when do these flaky tests become flaky? For instance, if they are flaky right from the start, when the test is introduced to the code base, we could basically focus our detection efforts for these flaky tests on those commits where tests are added to the code base. The way how we investigated this was basically by looking at the commit history of the flaky tests. We looked at all of the individual timelines for the different tests, and we were mostly interested in 3 specific commits. First of all, we looked at the latest commit, which is rightmost here in the figure. And we tried to identify whether tests are flaky. Then we had a set of flaky tests that we know are flaky. And for these flaky tests, we basically identified the test introducing commit on the left-hand side, the yellow dot. And somewhere in between there, between the test introducing commit and the latest commit, there must be some commit where the test actually turns flaky. And we tried to find that. Specifically, what we did was a 4-step approach. First of all, we ran existing flaky test detectors on the latest commit for numerous Java projects. Then after this, after we had identified flaky tests, we categorized them. This is important because flaky tests may have different root causes. And we wanted to make sure that when we are looking at the test introducing commit and we find the test to be flaky, we wanted to make sure that it's for the same reason, because we wanted to know which detector we need to apply. Would we find it with the same detector or not? Then after categorizing these flaky tests, we basically went back in history in the time and tried to find the commit where the test had been introduced. And after that, we essentially used git bisect with the detectors to find the commit where the test actually turned flaky. This was more challenging than we thought, because of course there is a certain non-determinism in flaky test detection, and sometimes we were a little bit off with finding them. So a purely automated approach did not work. We had to add manual inspections as well to precisely identify the flakiness introducing commits. For all of this, we used different tools. For the initial identification of flaky tests, we used 2 common state-of-the-art flaky test detection tools, that is ID Flakies and Nondex. And these 2 tools are capable of finding flaky tests that would be found by the 3 detectors that I introduced earlier. For the categorization, we had to be a little bit more precise. The problem in that sense is that ID Flakies is too powerful. It is capable of identifying flaky tests that are flaky when, or that fail when run in isolation, and that fail when run in different orders. So it has these 2 functions basically. And in order to precisely categorize the flaky tests that we found, we split that functionality up in the 2nd step. And we tested specifically for isolation, and we approximated order-dependent flaky tests by running tests one by one. What we mean by that is that we took all pairs of tests in the test suite, and we took all of the permutations of these pairs. So for each pair of tests, we checked for both possible orders whether they make a test fail or not. Here are the results. The table splits up the flaky tests that we found to be also flaky on the test introducing commit by the different types of flaky tests. I would like you to focus on the right-hand side of the table first, where we see the total number. So 245 tests were found to work actually on the test introducing commit, and we were able to use the detectors. And out of those, 184 were found to be flaky on the test introducing commit. That means right from the start. And that's 75% of the tests that we were able to analyze. So that's a pretty big number, and also pretty good news for flaky test detection, because it means if we focused the detection efforts on for these projects in our study on the test introducing commit, we would have been able to find 75% of the flaky tests. What we also see is that there is a bit of variance in the success rate, so to say, across the different classes of flaky tests. The left columns, the 3 left columns, basically are corresponding to the different detector types that I had introduced. The left-hand side, so you already know from Martin's talk what an order-dependent victim test is now. But just to remind you, these are the ones that are really order-dependent. That means they fail because there is another test in the test suite that makes them fail. Then the second column are the brittle tests. These are the ones that fail in isolation. And the third one are the ones that are found with non-dex that have deterministic implementations of underdetermined specifications. The last column, ND, is basically a summary column for those cases where we couldn't really say what the category is because the tests were failing under different conditions in our study. What's interesting here to see is that the numbers differ quite a bit. So usually for the OD brittles and the ID flaky tests, the success rate to find them on the first commit is even higher than the average that we found. Whereas for the OD victim tests, the order-dependent flaky tests, it is lower. We looked into this a little bit more, and what we found out was that in most cases, the test introducing commit did not contain this additional test that is required to make the test fail. That was only added later. So the takeaway from these results is it is rather effective to run flaky test detectors on the first commit when the test is introduced. However, what we also see is that 25% of the tests are not flaky when they are introduced. That means 61 out of 245. So what do we do about those? Can we learn something more about them when they become flaky so that we can steer our detection efforts? It turns out we can, at least for some of them, because 24 of these 61 become flaky when their test class is modified. So that means if we basically expand our testing effort and focus it not just on the commit where the test is introduced, but on every subsequent commit where the test class of that test is modified, then we can also identify these 24 flaky tests with relatively low effort. And that basically boosts our success rate from 75 to 85% of flaky tests that we could find with relatively little effort. Now, for the remaining 37 tests, we basically tried to find correlations with different factors so that we can identify when they turn flaky, but we couldn't really find like a clear pattern for that. So the only thing that we can do is we can recommend developers and companies to test infrequently, to repeatedly test infrequently. What we can add from our data is some insight that, regarding the frequency, because what we see here on the right-hand side are the cumulative distributive functions for the commit distances between the test introducing commit and the flakiness introducing commit. And we see that they are vastly different for the different types of detectors. The red line here, for instance, shows that we can find 85% of the ID flaky tests, that means the ones that have underdetermined specifications or fail due to underdetermined specifications, within 254 commits. Whereas for the order-dependent flaky tests, this is quite different. So we start with and are able to actually identify in our data set 18% of them within 38 commits from the test introducing commit. However, then there is a steep increase in the commit distance. So to go up another 17%, we would need to increase the distance for checking again to 2,273 commits. And it becomes even larger if we want to detect 50% or even 100% of them. So the advice that we can give here is that for ID flaky tests, we should check soon, relatively soon after they have been introduced, whereas for order-dependent flaky tests, we should basically start and then slowly decrease or increase the commit distance with which we are rechecking. To briefly summarize, I have covered in the talk what flaky tests are, why they are a problem. I have given an overview of our study, how we try to find out when flaky tests become flaky so that we can steer detection efforts. I have presented results. We found that 75% of the flaky tests are flaky right from the start, that this number increases to 85% if we are looking at test class modifications, and that it largely depends on the type of detector, what other strategy to follow in order to efficiently detect flaky tests. If you're interested, please take a look at our paper that was published at UPSLA 2020 and presented there by my colleague Wing. And I'm happy to take any questions.